Simple harmonic motion is one of those places where calculus pays off really fast and easy. So you can do all these derivations without calculus, but they're a little bit more weird and involved, or you can just use the formalism straightforwardly, and that's what we're going to do here. This is nominally optional at this stage, depending on whether you've taken enough calculus to have done derivatives of trig functions. If you haven't done that, then put this to the side and come back to it later in the year. But before the exam in May, you're expected to be able to do some calculus, and this is the kind of place where they ask you to actually do some. So let's walk through it. Let's say we start with a mass m attached to a spring with constant k, sliding along a level frictionless floor. At any moment, the spring has been stretched a distance x, or it's been compressed if x is negative. So our picture is sort of, we fix the spring at one end, and we say that our spring starts off like this. We'll call this x equals 0. But now I have stretched it, and it's at some position x. Of course, that means its free body diagram looks something like this, where there's a force pointing this way. And of course, the ones that we're not going to worry about, there's a weight and a normal, but they'll just cancel out because it's horizontal. So ma is equal to the force, and we can say at this point I'm going to say a is just the acceleration. I'm not going to draw it because I don't want to include its direction. I'm just going to say, what is the acceleration going to be? And we have that, of course, ma equals f net. But if the thing's been stretched to distance x, then of course the force is oppositely directed, and a is the second derivative of x. Right, way back when, a is dv dt, but v is itself dx dt. So we have the derivative of x, which is the second derivative of x, written in that kind of bizarre d squared x over dt squared notation. Thank Leibniz for that, I guess. So we end up with m times d squared x dt squared is minus kx. Then we can do some stupid algebra tricks, divide out by the m, bring everybody over, and we get that the second derivative of x plus k over m of times x equals 0. And this is some magic in mathematics. This is a second order homogeneous differential equation. Right? It's a differential equation because of that, right? Because of this, the fact that there's a derivative. It's homogeneous because there's no function of t here. It's ordinary because the derivatives are ordinary derivatives. And most likely that doesn't make any sense to you unless you're taking Calc 3, but we're saying that we have dx dt, not round back d, round back t. If you don't know what the round back x notation is, round back d, then don't worry about this. It's just a different kind of differential equation called a partial differential equation. And we're saying here that it's not that. And it's a second order differential equation because of the squares. The second derivative. Not really the square. All right. This is not the simplest kind of differential equation, but it's pretty close to it. It's eminently within our ability to do it. We need to find a function whose second derivative is proportional but opposite to the function itself. Matched to the idea of a differential equation would be an ordinary algebraic equation, something like x squared plus 3x equals 0. And solving an algebraic equation means finding a value of x such that the equation is true. Of course, we know could be multiple values, but finding all the values of x such that it's true. Solving a differential equation means finding a function such that the equation is true, or really all such functions. So we need to find a function whose second derivative is proportional to the function itself, but is of opposite sign. The easiest way to do any problem, of course, is to already know the answer. This gets a fancy name called the Ansatz, which is German for, I think, answer. Or, no, it's not answer, something else. But it ends up, it's a method that says, let me propose what I think it's going to be and see what would have to be true for my solution to be correct. Thus, it's not that much removed from just guess and check, but it's a little bit more sophisticated. The guess we're going to go with is the one we've already seen from earlier work, that x is some cosine. So it's some number times cosine of another number. We take our first derivative, and of course the derivative here, a comes outside. Derivative of cosine omega t is minus sine omega t times the derivative of the inside. So we get minus a omega sine omega t. And we take our second derivative, so we do it again. The minus a omega stays here. Derivative of sine omega t is cosine omega t times another factor of omega, so we end up with the minus a omega squared. And then we recognize that we could factor this to be minus omega squared of times a cosine omega t, but that was x. So when we go back into our equation, if we plug this back into this equation, we end up getting minus omega squared x plus k over m x equals 0, which will work for all values of x if omega is root k over m. By the way, as an aside, or omega is minus root k over m. And we're going to neglect that because we're going to define our frequencies as being well-defined only if they're positive. Not a math limitation, but a physics limitation that we want omega greater than 0 physically. It's a counting thing. You can't have negative counting things. But what is this omega? Well, when the time increases by big T, that is 1 period, the argument of the cosine should increase by 2 pi, because cosine is periodic on 2 pi. Put another way, that delta of omega t should be 2 pi when delta of t is capital T. That when we increase the time by capital T, we increase the argument by 2 pi. But delta is a linear operator, and omega is constant, so it comes out front. So omega t equals, delta of omega t is the same as omega times delta t. But we just said that delta t is big T. So we end up with maybe the most important result here, omega t equals 2 pi. So omega is 2 pi over t, and t is 2 pi over omega. As an aside, notice that this implies that f is 1 over t, then f is 1 over 2 pi over omega. So f is omega over 2 pi, often written as omega is 2 pi times f, which is why we call omega the angular frequency. It's the frequency multiplied by the 1 cycle angle, which is 2 pi. That's the 2 pi that's coming from 2 pi radians that will be W for the rest of your career in mathematical and scientific applications. We can look back to our earlier result that omega is the square root of k over m, and combine it with the fact that t is 2 pi over omega to derive what we had earlier before, the mass period relation, that the period is 2 pi square root m over k. And so we're satisfied, mostly. It would take only a few moments to show that x equals b times sine omega t is also a solution to the differential equation with the same omega. It takes a little bit more to prove that there are no other solutions, although it can be shown. It ends up there can only be 2 independent solutions because it's second order. So much like we know that the order of a polynomial tells you how many roots it has, the order of a differential equation tells you how many distinct independent solutions it has. There's a lot of work that goes on in Calc 3 to talk about, or Calc 4, depending on when you hit it, about what does it mean to be independent and how do we test that and so on. It more or less covers what you think. It turns out that any solution to the differential equation that we have could be expressed as a sum of sine and cosine, according to this, that x equals a cosine omega t plus b sine omega t. All functions that do solve the differential equation could be written in this form as well. Let's look at 2 special cases. Special case 1, the mass is pulled a distance L from the equilibrium released from rest. So x of 0 equals L. Oops. And v of 0 equals 0. we plug into the x equation first, and we say that L is, remember, because our equation is x is a cos omega t plus b sine omega t. So when t equals 0, we get cosine of 0 and sine of 0 respectively. But the sine of 0 is 0, so this term disappears. And the cos of 0 is 1, and we find that L equals A. Not surprisingly, the amplitude of the motion is where we have what we have in front of the cosine term. Right? No big deal. And then we go and say, well, our derivative, remember we have that the velocity, is going to be the derivative. That v equals minus a omega sine omega t plus b omega cosine omega t by just simply taking the derivative of the position equation. And we want that to be 0 at time equals 0. So now we'll have minus a omega sine 0, and this term will go away. And then we have that this, of course, is b omega cos of 0, which is 1, which means 0 equals b omega, but omega can't be 0, so b must be 0. So the full solution is exactly what we would expect. We pull it some distance and let it go, and it's just that distance times cosine omega t. Special case number 2. The mass is given some sharp impulse at the equilibrium location, such that t equals 0, x equals 0, and v equals v0, some initial velocity. We do the same kind of trick, and here we get that 0 equals a, cos 0, which means 0 equals a. So the cosine term has dropped out. And when we plug into b, remember now a has gone to 0, so this whole term is gone without even thinking about it. And we have v0 equals b omega cos omega t. When t equals 0, this is cos of 0, which is 1. So v0 equals b omega. So we end up with that b equals v0 over omega. And so the solution is only the sine solution, and the amplitude of the motion is its maximum velocity or its initial velocity over omega. And that's kind of interesting.